and then you switch the correspondence to figure out what you compare it to.
Shouldn't that p right on p, the interval p or whatever, shouldn't that be 2xz instead of 2xy?
Oh, yeah. Okay.
Points.
All right, point for error. Okay. All right. Okay. Okay, now we're good. All right, so now let's take this and differentiate it with respect to y and z. So fy is going to be partial respect to y of x squared z plus x y squared plus g of y z. And this is supposed to be equal to q. So we get, well, 0 plus 2xy plus partial g with respect to y, but it's equal to 2xy. Because that's what q is. So g is independent of y. Gy is equal, dg dy is equal to 0. So that's one thing we know about it. But now we need to check partial respect to z. So it's dbz of x squared z plus xy squared plus g of yz. And that should be equal to r. So we'll get x squared plus 0 plus gz. And that should be equal to x squared plus 3z squared. So gy is 0, gz is 3z squared. So with that in mind, what does g have to be?
Just take the integral of that.
Yeah, so what you can do is, so gz is 3z squared, so g of yz is going to be antiderivative with respect to z of 3z squared. So it's going to be z cubed plus some function that's independent of z, so it's a function of y. But gy is 0, so this has to be a constant. That's the only possibility. All right, it can't depend on x, can't depend on y either, and the z dependence is already taken into account. So the only choice left is it has to be a constant. So now we have our function little f defined completely. F of x, y, z is equal to x squared z plus x y squared plus z cubed plus any constant. And if you take that function and compute its gradient, you can verify that. You'll find that you'll get exactly these components of this vector field.
How did you know h of y was, how did you know it came to a constant?
Oh, because we found that because the derivative of this whole thing with respect to y has to be 0. Yeah. Yeah, so really, yeah, we're using both pieces of information to finish the job.
Will k ever come into question?
Not really, because what's going to happen is when you use it in the fundamental theorem of line integrals, which I'm going to do in a second, you'll find it just cancels out. All right, so let's use this for a line integral. Okay. So we're going to compute the line integral of f over a curve C, where C is defined by this parameterization. X is equal to t squared, y is equal to t plus 1, z is 2t minus 1, and t runs from 0 to 1. So, now that you know that f is conservative, and you know exactly what function big F is a gradient of, you can just jump directly to the conclusion from a fundamental theorem of line integrals. It's going to be little f of r of 1 minus f of r of 0. Right? The 0 and 1 are your beginning and ending parameter values. So you only need to compute the coordinates of the beginning and ending points of your curve. So we just need to plug in t equals 0, t equals 1. Alright, so here we get 0, 1, and minus 1. So this is beginning point, 0, 1, and minus 1. The ending point is going to be 1, 2, 1. And now you'll plug these into your function f that we got, x squared z plus xy squared plus z cubed, evaluated at, so you plug in x, y, z equal to these 2 points, and that's it. So once you know that this vector field is conservative, once you come up with the function little f whose gradient is your vector field, then you just evaluate this and you're done. I left out the constant k here because what's going to happen is it's just going to cancel out anyway. You can set k to whatever value you like. In this case, I just set it to 0. There's no reason not to, really.
What happens if it's not
In this case, unfortunately, what you have to do is, if you're given a parameterization of a curve, you have to fall back on the more direct way of evaluating this. You just have to grind this out directly, like we did before. Alrighty. So, questions about how you handle a conservative vector field. Alright. So given a vector field, if you don't know if it's conservative already, check to make sure that it is. To be anti-differentiation with respect to, you can pick any variable to start. And remember, when you're anti-differentiating with respect to one variable, you have to tack on a function that is dependent upon whatever variables you still have left. So that's something to be careful about. Especially when, with two variables, it's pretty straightforward. The anti-differentiating with respect to x, what's left is a function of only y. Whereas in this case, we had a function of y and z that we had to figure out what it was. Then we take that and anti-differentiate that with respect to z. What's left can depend on only y because the x dependence is already accounted for.
So if your g sub y over there was like, say 1 instead of 0, then this over here would be ky?
Actually, if this was 1, then you would get y, so its partial with respect to y would be 1, plus a constant k.
Okay.
Yeah, yeah.
Alright. Okay, a little bit of time.
Alright. Now, so now let's take a look at something related to, from physics that's related to line integrals. And when we first talked about line integrals, how they could be used to describe the work done in moving an object from point A to point B along some curved path. So we'll come back to that context. So here's point A, point B, object being pushed along the path by